Hi, today we will start a new series concentrating on a different kind of experiment. And our goal is to go into some more advanced topics in quantum mechanics, topics that some of you have already heard about in popular literature, things like entanglement, non-locality, and things of that nature. And in order to illustrate and to understand these effects, we will start from a model system, which is a particle with spin. And we will, in today's clip, we will define what is this system, what can we measure, and why it's so interesting. Okay, so it was already known from the beginning of quantum mechanics that certain particles can have a magnetic moment. For example, an electron has a magnetic moment. Now, from where does this electric moment come? So in around 1908 or somewhere around it, the following picture was proposed. An electron, we can think of it as a particle, like a hard sphere. It has charge. This particle spins, turns around like if you have a ball that you spin it. Spinning it causes currents. These currents create a magnetic moment, and that is the explanation for the electron spin. A very nice name. Unfortunately, this explanation is completely wrong. Why is it wrong? We know nowadays that electrons are extremely small, perhaps even point particles. And the fact that the radius is so small, if not zero, means that if we spin it, the angular velocity needed to create this magnetic moment will be larger than the speed of light. Cannot be. So actually, the origin of spin is something else. It's a relativistic effect. It comes out of the Dirac equation. But for our purpose at the moment, we only state that particles, certain particles, for example, the electron, has spin. Okay, it has a moment. And if we think about it, this moment can be in any direction. So, from the classical point of view, in order to define the direction of the spin, we will need two angles, theta and phi, and that determines the direction of the spin, of the magnetic moment. Okay, in order to verify it, an experiment was conducted in the 1920s by two physicists, Stern and Gerlach. In this experiment, those guys had a source of, actually it was atoms that had a spin. They come out of the experiment with some velocity. There is a screen and they put in a magnet somewhere along the path. And their expectation was, since the spin will couple with the magnetic field here, and let's call this the z direction, the atoms coming out of this box will acquire velocity in the z direction, and on the screen we'll get a whole smear of region of electrons hitting, where the exact position of a particle hitting will depend on the angle of the magnetic moment compared to the z direction here. Okay, so that's our classical expectation. What was actually observed, and that was a huge unexpected result. They actually, a huge surprise, no one expected it. They actually saw 2 points on the screen, and that's that. Meaning that every electron coming, sorry, it was an atom coming out of this box had either a magnetic moment in the direction of z or in the direction of minus z. Only 2 values are seen in the experiment. So, from the point of view of quantum mechanics, we have either up no other values are seen, meaning that we have here a quantum observable that can acquire only 2 different values, up and down. Now, you can guess that because of the simplicity of this system, the fact that you can have only 2 measurable results, it became like our representative system for studying quantum mechanics, of course, due to its simplicity. Okay, so how do we write down quantum mechanics for this system? Well, we have only 2 observed measurable observations, up and down. Therefore, we have only 2 states in which the system can be. Either the system is up in the z direction, or it's down. So from the point of view of quantum mechanics, the Hilbert space of this problem has only 2 vectors. It's a 2-dimensional Hilbert space. We can, of course, represent them as also in the usual vector notation, 1, 0, and 0, 1. What can we measure? Of course, we can measure the magnetic moment in the z direction. So the corresponding operator will be a 2 by 2 matrix. Of course, our dimension here is 2. And that's that. We can also measure the system in the x direction, meaning we rotate our magnetic field here in 90 degrees and measure that case. And in that case, The operator has the following structure. It's again a 2 by 2 matrix with these values. Okay, let's see how it works. Let's say we want to know what is the average value of the spin in direction z for the case where the particle is prepared in a state where it's in the z direction. Okay, we go do the mathematics. And we acquire the value of 1. We do the same calculation in the x direction. You can just plug in the vectors and the matrix, and you'll get 0. Why is it? Because if I know that the system is in the direction z, I don't know whether it's pointing in the direction of x or minus x. Therefore, on average, it gives us the value 0. Okay, so far, it's a nice toy model for doing quantum mechanics in the simplest mathematical way. But there's nothing yet new compared to what you have familiarized yourself in other systems. In the next clip, we'll go into the case where we are considering 2 spins. And in this case, we'll start to see interesting things emerging. Okay, so until the next clip, we'll move on to something more interesting. Thank you.